Thank you very much for the kind introduction. Thanks a lot for inviting me to give a keynote at the ICRA 2021. I wished I could be in Xi'an these days to give this talk in person, actually. But we know that this is a difficult situation, but I'm very honored actually to be here and to report about my work. In particular, today I'm going to talk about learning humanoid manipulation from humans. First of all, let me thank my team actually conducting all the work, most of the work I'm going to present, and also my family for giving me the opportunity to spend so much time with my research. So when we talk about manipulation, actually, for me, the manipulation and intelligence of an artificial system, but also biological systems like humans, are inseparably intertwined. So manipulation is the ability to perform actions which change the world. Yeah, it's the ability to physically interact with the world and to change the state of the world. And intelligence of a system is the ability to detect such change and to adapt to the change, to new situations, to predict action effects based on experience, for example. And this is one of the key things I believe, or one of the key abilities for robot systems, which has to predict, to act, and interact in open-ended environments. I have been working on humanoid robotics since 20 years, and we did a lot of work related to manipulation. Just to give you a few examples, our ARMA robots, the ARMA 3 and the ARMA 6 here, performing complex manipulation actions in a kitchen environment, like interacting with doors, opening doors, closing doors, manipulating objects or cleaning objects, and so on. But manipulation is not only about really control and linking perception and control strategies. Manipulation requires a holistic approach which integrate control, integrate perception, integrate machine learning, and AI methods. You see here another example of a humanoid robot, which is helping a human to prepare dinner for 2 people. And Arma, please help me to prepare dinner for 2 people. This is a very simple sentence for us, but what's behind it actually, the understanding what help means and the understanding what's needed, which objects are needed to set up a table to prepare a dinner for 2 people. This requires planning, this requires action execution in a robust way, and manipulating of different objects, where of course grasping of these objects is a prerequisite for manipulation. But in this talk, I'm not going to talk about grasping, I'm going to talk about manipulation. Another example of collaborative manipulation, where a humanoid robot can infer the need of help of a human in order to support a technician, as in this example here, in maintenance and repair tasks, where single-handed bimanual manipulation actions has to be executed in order, for example, to lower the guard, as you see in the video, or to transport it jointly or together with the human to a given placing position. We did recently a lot of work on collaborative human-robot manipulation, as you see also here in these examples, not only removing the guard and placing it, but also grasping the guard again, manipulating it, and inserting it into the conveyor belt. When we talk about manipulation, a very important thing is, of course, force. Yeah, because manipulation requires interaction with the scene, interaction with the objects, and therefore force is an important modality, sensory modality, and important information which must be considered. You see here examples of force-based manipulation tasks in contact-reach activities, where the robot is cleaning the table or cleaning an arbitrary curved surface. But this is work which is done in kitchen environments, in industrial environments, but recently we're working on manipulation tasks for the decontamination of nuclear installations. So actually cleaning contaminated objects, as you see here in these photos here. This is how decontamination of nuclearly contaminated objects is done today. And the question is how robotic technology, and in particular, in our case, humanoid robotic technology, can contribute to this very challenging, but also for the improvement of quality of life of humans, very important task. So as I mentioned in this talk, I'm going to talk about learning manipulations from human observation. And when we think about it, we have to observe human. We have to actually, based on the observation of humans performing manipulation tasks, to build generalized representations of the task, in particular, actually, while taking into account the constraints in the tasks. For example, the relations between different objects. And once these representations are learned, it is then the next step is to execute them in the real world, to adapt them to the given situation, to evaluate the success of the execution, and to learn actually from the experience of the execution in order to refine some models related to the strategies, how these tasks must be performed, or models related to the robot itself, actually. And we are interested in learning semantic task models. Semantic task models means that we are interested in learning models from human observation, which combine symbolic task information like the actions, their sequences, the spatial relations between objects, hands, and tools used in the manipulation tasks, the temporal relations between actions, and of course, for a high level symbolic planning, pre and post conditions of such actions. For the execution, such symbolic information is not enough and sufficient, and therefore sub-symbolic information, so really the way how humans execute tasks are very important. And therefore, position, velocity, trajectories, but also force profiles in these manipulation tasks, geometric and kinematic constraints of the objects and of the robot itself, of environmental elements, are also very important. And I hope that in this talk, I will be able to give you some insights about what we are doing in these two areas of research. So since we are interested in learning this from human, we have actually to capture human demonstrations. This is what we are doing. We are capturing and reconstructing whole body and object motion in human demonstration in order to generate data to build a human motion database from which learning of these task models, but also of underlying motion primitives can be done. And the result of this work in the last 5 or 6 years resulted in one of the biggest whole body human motion databases, where, as you see here, we can capture local manipulation tasks of humans, so manipulation and locomotion tasks of single humans, but also multiple subjects here. Where we can automatically segment these demonstrations based on some segmentation algorithms for manipulation tasks, but as I mentioned before, for local manipulation tasks where both legs and arms are involved. And we are able also to do motion analysis, for example, to extract important parameters of the demonstration, like the center of mass, the angular momentum of the whole body, And the goal is to use this data as you saw in the video in order to do a retargeting or to generate motion for humanoid robots. But let me start with bimanual actions, actually, not with whole body actions. If you think about bimanual manipulation tasks and you would like to learn these semantic task models of bimanual manipulation, there are a lot of things which must be considered, like, of course, the body motion, of course, the grasp type, how the knife is grasped by the human, how the cucumber is held in the other hand. What are the relations between the board, the knife, and the cucumber? The head orientation and the gaze direction of the human. It is really a bimanual manipulation task, or it's just the only one hand executing this task? And very important, of course, what kind of contact information or contact forces are applied in the execution of such tasks. We have a motion capture studio, which is equipped with a multimodal sensor system, so marker-based motion tracking with Vicon, but also markerless systems like RGB-D cameras, microphone array, head-mounted cameras, data gloves, but also IMUs and force sensors. And with this, we collect all data, and in particular, recently, we actually collected a new data set for bimanual manipulation actions. As you see here in the video, these are only 12 actions of 2 people, but the unique thing about this data set is the variations, the intra and inter-subject variations in the recorded data. We believe that this is very, very important to bootstrap research in the area of bimanual manipulation and bimanual coordination. And you see here, all these motions are retargeted to a reference model of the human body. You see here in the animation, the reference model of the human body, which makes us independent actually of the teacher, independent of the person executing the task. But let me start. I mean, this is a recording of the data, but we have to understand human demonstrations, and therefore we developed methods which take into account both levels of segmentation of human demonstrations. On the first level, the higher level, semantic segmentation of demonstrations based on object-hand relation changes. Yeah, in particular, contact informations between hands and manipulated objects. But for the execution, we need this sub-symbolic information, sensorimotor information, and therefore we conduct a motion segmentation based on trajectory characteristics. You see here in the example, in this semantic segment where the cup is in the hand, you can lift it, you can pour, you can place it. And the other, on the top level, you see here the 2 other semantic segments where no contact between the hand and an object exists. And as you see here, we use actually this hierarchical segmentation method for the segmentation of manipulation tasks, but also of local manipulation tasks where the entire body is involved. Here is another example which show actually that in addition to detecting contact or non-contact relations between the hand and the objects, we have actually to segment or to learn these underlying motion primitives which are needed in order to execute the task. Here the lifting, and here the placing, where a contact between the bottle and the table is established. On the second level, we are of course interested in learning the characteristic of the motion, like shaking here, shaking the bottle here. And you see here the different examples here, or the animations, and also how this information is segmented. You see another example here for the segmentation of the bimanual actions, or for an example from the bimanual motion dataset, which I introduced before. Once we have that, we have to learn some representations which we can execute on the robot. I mean, the robot, we have to do, of course, the retargeting from human motion to the robot. I'm not going to talk about today, but we have to find the representations which are adaptable in order to actually implement cut, implement move, place, lift, and shake. And in order to do that, we introduce a new formulation of motion primitives, which we call via point motion primitives, where the demonstration or a skill of the robot is represented by an elementary trajectory, a spatial trajectory that connects two via points, for example, start and end point of a trajectory, and a modulation or a shape modulation term, which represent the probability distribution that models the offset from the demonstration to the elementary trajectory. And with these via point motion primitives, you can actually insert new via points in a previously learned actions without a complete relearning. For example, to reorient this object here to pass through this area, or to avoid collision with this object while grasping the other object. And these via points can actually adapt and generalize to task-specific constraints. You see here examples how the task constraints are mapped using mixture density networks here to motion primitive parameters in order to execute the throwing task. In the same way, for our bimanual manipulation tasks, you can learn adaptable via point movement primitives for different pouring actions, as you see here in the example. So this is actually, for us, it's a very powerful, or we consider that as very powerful and promising way in order to learn task models from human demonstration, where on the one hand, we have the semantic information. On the hand, we have also the motion information, which is needed for execution on the robot. But what's important actually for these task models, semantic task models, are relations. In particular, spatial relations between objects and the hand, but also support relations, static and dynamic relations, for example, support relations, and including or considering these relations is very powerful in order to solve difficult tasks like or related to action recognition, to manipulation in general, but also to prediction. And therefore, we are working on, or we worked on, extracting spatial relations from human demonstration. You see here an example where we use RGB-D information. So 2D bounding boxes provided by YOLO of objects, of course, known to YOLO. And in addition, also both hands, elbows, and shoulders, and the head of the human provided from OpenPose. So this output here is used as input for another component, which allow 3D bounding box instance tracking. So by combining the 2D class bounding boxes, the depth images, and by conducting some smoothing. And based on this information, we calculate spatial relations between each pair of objects, and in order to construct a scene graph. And this scene graph actually represent then predicates or represent the predicates of spatial relations and the human pose. So with that, you see here you see here again the entire system. These are the list of predicates. This is actually the enriched scene graph by the head and hand and position of the human body, but also all other objects in the scene. And this scene graph is used as input for a graph network in order to predict actually the action probability performed, for example, by the right hand in the context of bimanual manipulation. So we encode spatial relation in a scene graph. As I mentioned, the hands and objects are the nodes. The edges are relations between the hands and the objects. And this is used as input for a graph network standard encoder process, the encode process decode graph network with the update functions as MLPs, which are trained, of course, and where we use the sum for all aggregation functions here. And with that, you can actually get a prediction about the actions performed by the right hand, as I explained before, like the right hand is steering, and for the left hand, you get actually the actions performed by the left hand by just mirroring the scene graph and doing the reclassification again in order to get the left hand actions. And consecutive classifications of the same action class result then in an action segment. In order to evaluate this method, we collected another data set, this time RGB-D data set for bimanual actions. As you see here, the details, which is publicly available also, and conducted here an evaluation regarding the classification accuracy, where we showed that we can improve our previous work actually here in 2020 by adding hand and head and shoulder elbow positions of the human to 0.7 to an F1 score of 0.7 in a leave one subject out cross fault validation. So these are actually the spatial relations, but in particular in bimanual manipulation, it's very important to think about temporal relations. What are the temporal relations? How is the synchronization or the coordination between the left and the right hand? And the question is, how can temporal relations also be learned from segmented labeled bimanual human demonstration? Here we use the Allen relations, and these Allen relations actually specify the order of actions. For example, the precedence relation of an action to other actions, like an action is happening before another one, X is before Y, or an action transitions actually in the next one, like meets, but also the concurrency of actions in the sense which of course tell us something about the temporal coordination of both hands, like two actions are happening at the same time. Actually, they are in parallel, so equal, or they overlap, that one action is happening during the execution of another action. And the question is how to identify important temporal constraints and differentiate them from noise in the data. Of course, we would like to learn these temporal constraints and to enrich our semantic task models by temporal information about action relations, for example, in the context of bimanual manipulation. And the second question is how to deal with errors in the demonstration or in the action classification, and how to incrementally learn temporal task constraints based on first experiments or first demonstrations, how actually to learn a model which can be extended incrementally based on new demonstrations. And one idea, and this is work in progress, what we're doing here, is to encode temporal action relations from all demonstrations of a task in a graph, like the nodes, where the nodes are the actions, of course, with object information, and the edges, the number of observed temporal relations between the actions. For example, 50 times before relation and 10 times meet relation. And you'll get something like that in the context of bimanual kitchen manipulation task, where you have, of course, to identify all Allen relation, to search corresponding action pairs, and to construct this graph and to update this graph for each action pair recognized in the demonstration. But this graph, as you see here, contains a lot of information which is not useful, and I can tell you contains a lot of contradictions and potentially also errors. For example, the meets relation is of course very important for temporal for temporal coordination. It naturally occurs if one hand's action transitions into another, one hand transitions from one action into another action. It rarely occurs across hands, yeah, because the hands are not usually very precisely and perfectly synchronized with each other. And so the question is actually how to get the important and useful information from this initial graph. You can, of course, think about strategies to remove contradicting relations. You can think about how to find action chains which are connected by meet relations and add them to the new graph, because these meet relations where one action transitions into another action are very important. And of course, in bimanual manipulation, we have concurrent relations like equal, starts, finish, or these Allen relations, what I mentioned before, to add these concurrent relations to meets clusters, which can be identified in order to arrive at something which is usable and which is actually interpretable also for humans. Like lift the knife meets actually, or the temporal relation between lift the knife and cut the banana is meets. So this means lift the knife transitions into cut the banana, and holds the banana finishes with cut the banana. This is, as I mentioned, work in progress, and I hope that we will soon have results which we can present and show actually how this combination of spatial object relations and temporal relations can contribute to the enrichment or building of more sophisticated semantic task models of bimanual manipulation. So, but manipulation is actually not only about really generating motion. Manipulation is very much related to understanding, yeah? Imagine a robot at your home which should be able to understand natural language instructions like Armor, put the mustard on on the top of the rusk, please. This is a very, very simple natural language instruction for us humans, but for a technical system, for an artificial system, artificial cognitive system like a humanoid robot here, a lot must be done actually in order to be able to perform manipulation tasks according to these natural language instructions. Actually, we would like to generate actions which manipulate the scene, so change the scene, actually introduce change into the scene, which, as I mentioned before, this is manipulation for us. Manipulation is the ability to change the scene. And in order to do that, we need, of course, understanding of natural language. What is the target object? Okay, this is the button. What's the reference object? This is the rusk here. And what kind of relations should be established between the two objects, between the target and the reference object? This must be understood in natural language instructions, but it also must be understood actually in the perception. So from the scene, where is the rusk, where is the reference object, where is the target object? So we are interested, in other words here, in finding ways to communicate manipulation tasks to a robot on a semantic level, similar to what we humans do, yeah, and like perform a task in terms of fulfill some spatial relations between objects in the scene. So this means given a scene and a certain new relation like on top, we would like actually to find the best object placement or spatial relation or the action which actually realize this target spatial relation. In order to do that, we learn generative models of 3D spatial relations as parametric probability distribution based on cylindric coordinates. We combine here Gaussian and Fermi's distribution in order to get a representation with few interpretable parameters, which can be used actually in order to generate actions to realize the new scene, to realize the requested new relations. And these distributions are learned from examples demonstrated by humans. And once we get these distributions for the relation on top, as you see here, we can sample from the distribution to generate candidates for target positions of the target object. Once this is done, the robot can execute the task using a via point movement primitive, which can adapt, of course, to different locations and to different positions in the environment. And we can also do that for other relations. On top might be an easy relation to implement or to understand or to realize. But think about relations like move the apple T roughly to the left of the kernel bars. What does it mean roughly to the left? And these probability distributions of relation representations allow us to realize these things, as you see here in the videos. Put the apple T roughly to the left of the kernels, or put the apple T on the other side of the kernels. So this is an overview of our current research in the area of bimanual manipulation, but in the area of verbal scene manipulation. So manipulation of a scene based on natural language instruction. But as I mentioned before, we collected large-scale whole-body human motion database. And in the last part of the talk, I would like to spend a few minutes on telling you something about how we can use this data in the same way to generate whole-body motions. As mentioned before, the KIT whole-body motion database is publicly available for everybody. Please feel free to use it. And of course, generating of whole body manipulation motion for whole body manipulation, which include locomotion and manipulation, is a very challenging task, also due to the high dimensionality of the space. If we think about the human, or if we think also about a humanoid robot with legs and arms, this is, of course, a large space or high dimensional space where many of current motion planning methods will fail actually to generate, to efficiently generate motions for the robots. And therefore, we introduced in 2015 a taxonomy which describe whole body poses. This is a joint work with Julia Boras here. And in this taxonomy, we propose 46 classes or body poses, which allow us to describe a wide variety of human activities. And you see here, there are 18 standing poses, there are 18 kneeling poses, so where is a contact with the knee here, and 10 resting poses where there's a large surface of interaction with the environment. The most important thing, I'm not going into the details here about the taxonomy, that the lines in the taxonomy actually transitions between poses, represent transitions between poses. So you can transition from 1, 2 to 1, 1 by going through to 7, or you can go down to 3, 12 and up to 2, 2 and go to the single foot support position. This was a conceptual work, what we did at the beginning, and we started actually validating this taxonomy, these 46 poses of the human body, which are usually used by the human body based on the data we collected. And you see here an example of stepping the stairs, where a subject swings the left leg with the right foot, right hand support pose. And you see on the right hand, actually, this graph, which represent the poses which are needed in order to realize such motion. So you start with the double foot support, you lift one leg, then single foot support, double foot support, you touch the handrail. While touching the handrail, you raise other leg and so on. And we did that for a wide variety of local manipulation tasks, not only bimanual, but also, as you see here, locomotion and manipulation tasks. And in the video here, you see actually the poses from the taxonomy which are needed in order to execute or to generate a motion for this task. Also for balancing tasks, you see also here the temporal order, what kind of poses are needed and in which temporal order should be actually used or concatenated in order to realize straightforward walking or upstairs walking and so on. So the question is, what can we do now with this taxonomy and with this analysis? We can generate multi-contact whole body motions, because multi-contact whole body motions are actually nothing else than sequences of poses in our taxonomy. And here we use a statistical approach for the motion planning, or for the planning of these multi-contact motions based on the taxonomy and based on knowledge extracted from human observation. Actually segmented human motion, which are used in an n-gram, which is usually used in natural language processing and understanding to predict the next word in a sentence given the history of n-1 words. Here we use in particular 5-gram language models, which are learned from segmented whole body human motion. And we statistically learn conditional transition probabilities between different whole body poses for a model of the human body here, but also for our humanoid robot here in simulation. So with that, I would like to conclude with some remarks regarding challenges and open questions. I think learning manipulation task models on both levels, on semantic and sensory motor level, from human observation is a powerful technique which should be followed. And a very challenging question is, in general, in manipulation, how to achieve human level manipulation performance in open-ended environments. This remains a large and huge challenge for robotics in general. And I believe that we have to think more about representations of perception and action, which also combines semantics and syntax of manipulation actions. And I think learning such representations from human demonstrations or from human motion data is also very powerful. And last but not least, I believe manipulation research can benefit a lot from manipulation platforms. If you think about the introduction of several robot platforms, starting with the PR2, the KUKA lightweight arm, the Now robot, now the Franka robots, and so on, I think the availability of such robot manipulation platforms would significantly contribute towards making progress in this difficult but very exciting research area. With that, let me thank our funding agencies for their support for our research. And of course, thank you for your attention. Thank you very much.
Thank you, Professor Tamim Asfour. So we still have some time for question and answers. so the audience can either using the QA box to enter their question there, or they can also raise their hand. I can unmute them to ask questions. And also just to announce, we have this talk, I think online use Bilibili. Currently there are over 4,500 people just pay attention to your talk, Professor.
Wow. Okay, I'm so honored. Actually, I hope I didn't do big mistakes. Yeah, and the colleagues will not start complaining. Yeah.
No, you're doing great. You're doing great. So there's one question just coming from the QA. So thank you very much from Yong Yao Li. So he asked, what do you think of soft robot manipulation and the rigid robot manipulation? Maybe tell a little bit.
Yeah, this is actually also, thank you very much for the question. This is a very very nice question, and a very promising also research direction. I mean, taking inspiration from humans and from the human body, you know, our hands and our body is also soft, is not rigid like all these robots we are using in our research. And I believe that the area of soft robotics will contribute a lot also to many of the challenges in the area of manipulation. Nowadays, most of us, people who are not working on soft robotics, they actually try to build intelligence in terms of rigid hardware and software, yeah, putting that together. But I think soft robotics opens new way, because this morphological computation, how Rolf Pfeiffer actually calls that, would solve many of the tasks we are struggling with, right? Because you don't need, for example, to plan accurate grasps on objects, for example, because the hand will adapt actually to the shape of the target object. I think also soft manipulation or soft robots in general are very important, because they would lead to a safer interaction and acceptability of robots when it comes to their application in human-centered environments, in very, very close to humans.
Okay, thank you. So here comes the second question from Aldin Abdullah. Thanks for the very nice talk, Dr. Asfour. Could you please elaborate more on how you constructed the temporal task relation graph? Was it done manually?
No, it wasn't done manually. As I mentioned, we encode temporal action relations from all demonstrations in this graph, and we start with all actually relations as I mentioned, between action pairs, and then you will get this this very complex graph actually, where not all these relations are actually how do you say, not all of them actually are valid, yeah. And then you have to try, we try actually, as I mentioned, this is still work in progress. We try actually to remove contradictory relations in this initial graph, and to update the graph so that we get something which is interpretable with that what we know about the human demonstration. So there are several steps. So we remove first contradicting relations. We find what we call meets cluster, so actions with transitions and actions. We try to find a cluster of these actions with these relations, and then we add concurrent relations like equal, starts, finish to these meet clusters if they are dominant and consistent with other existing relations. It's not manually done. Of course, we are applying machine learning methods here to do that, and it's still work in progress. But I'm happy to actually discuss with you longer about the details if you are interested.
Thank you. Let's move on to the next question. This one is from Ram Mamamothi. Many recent advances involving deep learning, for example, in the area of natural language processing, have depended on large data sets in the wild from millions of mobile devices, for example. You have shown very nicely calibrated and controlled data collection within the lab settings. What, in your view, will be the balance in the future?
Yeah, thank you very much for the question. I think, I mean, what we are doing, we are providing ground truth data for human demonstrations, for bimanual, for whole body local manipulation tasks. And this data can, of course, on the one hand, used to learn these task models, what I described today, but they can be used and already used, actually, for example, in the computer vision community as ground truth data for many other things. I would be actually extremely happy, and all my students and PhD students will be happy if deep learning can provide us with such reconstruction of whole body motion from pure 2D images. So maybe we'll get there at some point of time. I would be happy to use that and to enrich that, to enrich the data set in general. But currently, I don't see actually a way of generating such data in such accuracy as what we are doing here.
Okay, thanks. I see there's another question coming up from Qinxiang Zhao. Thanks for the nice presentation. I'm also researching interesting software robotics. What is your opinion on mounting a soft end effector on a rigid robot to enhance the degree of freedom?
Yeah, this is what many colleagues actually are doing. They're using soft hands on rigid arms. So far, I don't know of too many soft arms. Yeah, there are some people developing soft arms or continuum arms. So the parallel keynote of Jessica Burgner-Kars, for example, talking about continuum robots. But many people are attaching actually soft hands on their robot arms in order to solve many of the grasping tasks or manipulation tasks, as I mentioned before. So the group of Oliver Brock at the Technical University of Berlin, of Antonio Bicchi, for example, in Italy, but also many others in Yale and at different places. I think this is a good way if you find a way to control your soft hand in an appropriate way, then this would be fantastic. Yeah.
Okay, thank you. I think there's a sixth question. Do you plan to explore higher level scene understanding guided manipulation, like finishing some tasks by changing the semantic information of the whole scene through scene graph? For example, a robot cleaner cleans the tools on the table so that the table can change its dirty state into a neat one.
Yeah, thank you very much. This is one of the things actually we are working on, how to go up, let me say, in this architecture to higher level representations and semantic scene understanding combined also with natural language, as I mentioned today. And therefore, we are developing, or we believe actually that memories, in particular episodic memories, are very important in this context. And this is why we are developing a memory system which should bridge semantic symbolic representations and sensory motor representations. And this episodic memory, we can actually update the scene graph about relations. This is not implemented yet, but it's work in progress, where we can update actually relations, affordances of objects, pose of the human, so that yeah, you can do more reasoning. You can generate domain descriptions for symbolic planning based on these representations.
Okay, thank you. I think maybe there's one more. Let me see. I saw there's a 7. Oh, that's the 7. Let's see, based on the time. We're just a little bit over time. I hope you don't mind.
Yeah, so people actually who have questions, I would be really very happy to meet with you and to discuss. Just drop me an email. I think you can find my email on the web. I see many interesting questions regarding the taxonomy. So please feel free to contact me, and I would be happy to discuss with all of you about that.
Okay, I just found there's one more. Maybe make this the last question. Do you mind?
Yeah, sure. I'm here. I'm ready. I'm available.
Okay, sorry. So thank you for the nice talk. The human data set with the taxonomy is really interesting. However, human use much more than hands and feet for manipulation. Are there any insights on how to make robots more aware of their embodiment body for manipulation?
Yeah. Yeah, thank you. Thank you very much. Very, very nice question. Yeah, actually, this is, of course, the robots are somehow aware of their embodiment in terms of their kinematics and dynamic models, right? But this awareness, what we really need is something which you could compare to the body schema, what humans have as a representation of their embodiment, yeah, and of their bodies. I agree with you. Of course, we use hands and feet more, or they are the dominant, let's say, end effectors in all manipulation actions we perform. And there are, as you may know, a lot of work also on how do you say, on also formulating and representing hand actions, yeah, because, and we were really very inspired by grasping taxonomies when we designed or we proposed this whole body taxonomy. And I think what would be really great and important is to have a way how robots can adapt their own representation, body representation on the fly. Yeah. There are some people working on that. I mean, from classical point of view, of course, this is adaptation and parameter identification. From a more cognitive systems point of view, this is incremental or continuous learning and adaptation of body schema representations.
Okay, thank you. Yeah, I think that's all the question from the Zoom. There's just a one pop-up from that 4,000, over 4,000 audience there. I hope it's just maybe that's the last one. So I just asked whether your work involve task and motion planning questions.
What was the question? Sorry.
So whether this research will involve task and motion, I think motion planning.
Yeah, actually, when I started my work, I was doing a lot of motion planning indeed. So RRTs and PRMs and all the stuff, what you know in the area of motion planning and grasp planning. But of course, if we are interested in more intelligent behavior and semantic understanding of things, then we have to think about linking these motion planning approaches to task planning, to symbolic representations. Yeah, we are not experts in this area. Of course, this is needed without doubt, but there are a lot of colleagues. So there was a very nice colloquium at the IFRR Robotic Colloquia last week from Lorenzo Thomas from MIT, who talked exactly about combining task and motion planning. There are also people in knowledge-based AI or AI-enabled robotics, like my colleague Michael Beetz, who is also working a lot on task models or symbolic representations of things. But also, again, of course, this bridging the two words, yeah, the symbolic representation, sub-symbolic representations has been always a very challenging thing.
Okay, thank you. I think we are already turning your keynote session almost into plenary. It's almost 1 hour now. I think I have to conclude this session just because there's a couple of minutes they have to start another session. So I'm going to take this opportunity to thank you, Professor Tamim Asfour, for your wonderful presentation. And also there's very good interaction with the audience. So we have over 80 on the Zoom and over 4,000 on the Bilibili. So it's a great crowd here today.
Thank you.
Thanks, and hope in the future we can have more discussions on manual manipulations and many interesting research you did.
Thank you. Thank you again for inviting me, and all the best for the conference, in particular for tomorrow. Tomorrow is the Presence Day, right?
Yes.
And enjoy it and stay safe and healthy.